the problem looks like this. So we're on the second method. Rn2L about the center of mass. We have a plank that's fixed here. So it can rotate about this pin. And this is the center of mass. We have this 100 Newton force. All of these distances are 0.25 meters. And we want to calculate the angular acceleration. Okay. So first, we can calculate the moment of inertia about the center of mass. That is, this is a rectangle. This distance here is, what was it, 0.2, I think. So we have 1/12 times the mass, which was that 30? Times the quantity length squared, so 1 meter squared, plus width squared, 0.2 squared, and you get 2.6 kilogram meter squared. And do we have to use parallel axis theorem at all for this one? No, that's only if it's somewhere other than the center of mass. So this is it for the moment of inertia. And now we're going to go on to rotational Newton's second law and possibly Newton's second law. So first we have to draw a free body diagram. So where are there forces acting on this? So for one, gravity is always acting, but in this case, in this problem, that's out of the plane that we're dealing with. And we're doing this as a two-dimensional problem. So gravity doesn't show up. There's the 100 Newton force. And then there's one more place where something external is touching the outline of this body. Where's that? The pin, right? So we have this force F. And for this one, I'm going to choose the coordinate system at the center of mass. But you don't have to change where the coordinate system is. We could keep it where we kept it in the last problem. Sometimes it simplifies the math just a touch to have your coordinate system origin where your about point is, but it doesn't make much difference. Okay, so it's your choice where that goes. And now I'm going to set up the table. So professional, aquanauts, row for money. This and this? Yeah. Everything's a vector, yeah. This is the coordinates of the point where the force is applied. The coordinates are a vector, yeah. It's a vector, it's a position vector from the origin. So like if we're dealing with this force, then this is that p vector. Okay, so I'll start with that force F. Its location is 0.125, 0.217, And I'll try not to do this too much because I hope it doesn't confuse things, though. Like, I'm going to sometimes, when we're doing problems in the plane, I'm going to sometimes write things with a z component and sometimes just leave the z component off. And that's just going to happen because all of the rotational vectors have only z components when you're in the plane. Okay. What's the about point in this coordinate system? Yep, it's the center of mass, and that's at the origin, so that's just going to be 0, 0, 0. And so that's not going to change as we go down this list, no matter how many forces you're dealing with. So now this minus this gives us the row vector, so we have 0.125, 0.217. The force vector, we don't know anything about that direction. That's a pin joint, so I'll just call it fx, fy, 0. We're doing it as a plane problem, so it's a 0 z component. And now the cross product of that, this minus this, in the z direction gives us 0.125 fy minus 0.217 fx. And now the 100 Newton force. I'm going to move that force along the line of action just so I don't have to figure out that, the geometry would be a little bit of a nuisance to figure out what this point is. So I'm going to just move it. I'm going to just move it to the center here. And then that location is negative 0.125. Negative 0.217. The about point stays the same. Do that subtraction and you get negative 0.125, negative 0.217, 0. And the force vector, that is negative 86.6, positive 50, 0. Take that cross product, that minus that. Come on. Gives you 0, 0, negative 25. Okay, so I'm going to use Newton's second law and the rotational Newton's second law. This is, so add those two vectors up, that gives you the left side of Newton's second law. Add these two vectors up and it gives you the left side of the rotational equation. So Newton's second law says fx, fy, everything in the z component's in the z direction is going to be zeros, so I'm just going to leave it like this. Plus negative 86.6, 50 is equal to the mass, 30, times the acceleration vector of the center of mass. So that's two equations. And then the rotational equation. About the center of mass. I'm just going to write this as a scalar equation because we have all zeros in the x's and y's. So we get negative 0.217 fx plus 0.125 fy minus 25 is equal to the moment of inertia, 2.6, times the angular acceleration. And that's a third equation. Okay, so can we solve this system for alpha? No. And we can't solve it because if you count up, I mean, this is the analysis you should always do when you have a system, and it's easy to do. So we have fx, fy, a comx, a comy, and alpha. Okay. So 5 variables and 3 equations. So now what do we do? Yep, exactly. We're going to come up with 2 geometric constraint equations. And before you think about this mathematically, just what constraint is there on the motion that you can see? That's what we're looking for. So we didn't have to do this with when we did the rotation about the fixed point. But right now we're not assuming that there's nothing in here saying that that fixed point is fixed. So we just want a way to say, make sure that acceleration at that pin is 0. Okay? And also the velocity has to be 0 and the position has to be 0, but those, we won't need those for the constraint equation. The acceleration is the one that is going to help us. Okay, so how are we going to represent that? I mean, basically these constraint equations, what do we need from these constraint equations? We need 2 more equations without introducing any more variables, right? Or 4 equations and introduce 2 more variables. Somehow we have to get 2 equations ahead of the variables from where we are right now, right? So that would be, we need 2 geometric constraint equations without introducing new variables. So can you think of a way to represent the acceleration at that fixed point using the variables that we already have? That's sort of the challenge. And the way we're going to do that is the acceleration of, if we call this point F, okay, move it up here. Call this F. So the acceleration of F relative to the origin, which is just, that's the acceleration of F, is equal to the acceleration of F relative to the center of mass plus the acceleration of the center of mass relative to the origin. Okay. So what that says is we're going to break this up into, to calculate the acceleration of F, which we know is going to be equal to 0, 0. We're going to separate it into a kinematic problem where we're assuming that the center of mass is fixed. Okay, that's what this is. Like just the rotation of F around the center of mass and the acceleration of the center of mass. And that acceleration of the center of mass is already given by our equation. So this is this. Yes, but it's not, our coordinate system origin is fixed at that location, okay? We're doing this all with a fixed coordinate system. So the acceleration isn't going to be zero. Like, think of, so we chose a spot to put our coordinate system, and it's the instantaneous position of the center of mass. But this thing is going to accelerate by it. So, okay, does that sort of make sense? Yeah, exactly. Exactly, yeah, that's right. And if we didn't do that, then we'd have to use one of those corrections for calculating the acceleration in a non-inertial coordinate system. Okay, so this is the easiest. We're pretty much going to always want to have a fixed coordinate system. Okay, so what we need to calculate is this, okay? And to do that, we're going to recognize that the acceleration of F, assuming a center of mass fixed, is equal to the angular acceleration cross r plus omega cross r. Okay, so what that's saying is if the center of mass is fixed, then that F is just moving in circular motion around the center of mass. That r vector is the vector 2F from the center of mass. So that r vector is equal to 0.125, 0.217, 0. So the acceleration of F relative to the center of mass is equal to 0, 0 alpha crossed with 0.125, 0.217, 0. Plus, did we give this thing an angular velocity at the start? I can't remember. Okay. So plus 0, 0, minus 15. Crossed with 0, 0, minus 15 cross 0.125, 0.217, 0. And this is an equation we're going to use often enough that it would be a good idea to program this in your calculator where you can just enter, you can enter three vectors, omega, say, alpha, and r, okay? And it'll just calculate this acceleration vector for you. Okay, so if you calculate this cross product, you get negative 0.217 alpha, 0.125 alpha, plus negative 28.125, negative 48.825, this is the green. So now we want to add it to the red and set that equal to 0. So the fourth and fifth equations are, let me do it in order. So negative 0.217 alpha, positive 0.125 alpha, plus negative 28.125, negative 48.825, plus a COMX, a COMY is equal to 0, 0. Okay, it looks like sort of a mess, but all it's saying is relative to the origin, the acceleration of that point F has to be 0, 0. And we used the relative motion equation and the circular motion equation to get it. Okay, and we're pretty much always going to use those two equations. Those are where that constraint equation is always going to come from. So, okay. If you write this as a matrix equation, if you set it up this way, I'm just going down those 5 equations in order. Got 1 times fx, 0, negative 30. Let me just give you these numbers, and if you need to, you can go back and look at this later and ask me about it. So 0, 1, 0, negative 30, oops, 0, negative 0.217, 0.125, 0, 0, negative 2.6, 0, 0, 1, 0, negative 0.217, 0, 0, 0, 0.125, no, sorry, these two are wrong. So we have, for the last row, 0, 0, 0, 1, 0.125. Okay, so at that point, you just have to use whatever solver you're comfortable using. You're not going to want to have to do these by substitution, so you got to figure out something with your calculator. But you'll get that the force vector, that unknown force vector at the pin is 857.657, 1456.63. The acceleration of the center of mass is 25.702, 50.221. And then the punchline, this is what we were trying to ask for, what we were trying to solve, is negative 11.1667, which matches last time, so we don't have to do it again. So that's good. Okay, so where did those 5 equations come from? Just remind yourself. And then say it out of your mouth to let me know that you reminded yourself. First 2 equations were Newton's second law. Yep. The next 2 equations. No, the next one, right. The next one equation in 2 dimensions was the rotational equation. And then the last 2 were geometric constraints. Okay, so notice from this example, you can always use Rn2L about the center of mass, but you saw here the extra steps that it takes. You're going to save yourself a bunch of time if you have a fixed point to do Rn2L about that fixed point. So it's faster if you take advantage of fixed points when you have them. Any questions about that problem? Yeah. The matrix. Okay, so the next thing I want to do is I just want to give you a set of 7 steps for doing these problems. And these steps will translate to when we start talking about linkages, where we're doing this process for multiple bodies. You got it? Okay. So here are the steps for solving a rigid body problem. First, does the body rotate about a fixed point? If yes, your about point is the fixed point. If no, your about point is the center of mass. And this about point, let's call that A, your about point A. The second step, whichever one of these was your about point A, calculate the moment of inertia, I sub A. If A was a fixed point, or let's say if A isn't the center of mass, this will require the parallel axis theorem. Third, draw your free body diagram. And I expect to see a correct free body diagram anytime you use Newton's second law or the rotational Newton's second law. So that's, you'll lose points if you don't draw these free body diagrams on tests. And then fourth, set up that table. This you don't have to do, but like if you have a simplified problem where you can calculate those moments another way, that's fine with me. But this is where that table would come in. Professional aquanauts, row for money. Okay. Number 5. If A is a fixed point, skip this step. If A is the center of mass, though, you're going to use Newton's second law. So the net force is equal to the mass times the acceleration of the center of mass. Okay, you might need that and you might not. And the forces that appear in the table in this column give you this. Step 6, the sum of the moments about A is equal to moment of inertia times the angular acceleration. All of the things in this column give you those moments. And 7th, if for some reason, like that constraint equation, if you need the acceleration at a point P on the body, and we'll see that there's a lot of reasons that we're going to need this, then you're going to use the acceleration of P relative to the origin is equal to acceleration of P relative to A plus the acceleration of A relative to the origin. Where the acceleration of P relative to A is equal to alpha cross R plus omega cross quantity omega cross R. And notice for step 7, if A is fixed, then the acceleration of A relative to the origin is equal to zeros. And you get that acceleration just totally from that circular motion equation. Okay, any questions about that? So, you know, it's a little complicated, and that means that we're just going to have to do a bunch of problems. It's all of these problems have so much in common. It's just kind of a skill that you have to make your brain do naturally, you know. Okay, so let's do another example problem. Say that we're looking at this from a top view, and it's like a plank on ice. Say the length is 1 meter. The width is 0.3 meters. The mass is 15 kilograms. It's at rest at the chosen instant. That means, okay, well, first let me draw that. So the one force that we're dealing with is this 200 Newton force. It's at rest at this chosen instant, so that means there's no velocities and no angular velocities. But there are going to be accelerations because of that force. And let's call this point A and this point B. And we want to calculate first the acceleration of the point A, and second the acceleration of the point B. Okay, so first for part A, you can just go through these 7 steps. Is there a fixed point in this problem or not? Nope. This is just free to fly. So no fixed point. Use the center of mass. Okay, so now start at step 2 and calculate the angular acceleration and the acceleration vector of the center of mass. Okay. And then after you're done with that, we'll do part A, the geometric part of it, calculating the linear translational acceleration of that point A together, and then you'll do part B. Okay, so yeah, work on it on your own if it's making sense, but compare your answers to each other. Make sure you're on the same page. Feel free to ask each other if something's confusing, or ask me if something's confusing. Okay? So step 2, calculate the moment of inertia. So we're going to use 1/12 times the mass times the length squared plus the width squared. So I got 1.3625 kilogram meters squared. Step 3, free body diagram. Just looks like that. There's just that one force. What about gravity and the normal force? Those are just out of the plane. Like those are there, but they're not showing up in our plane analysis. Step 4, professional aquanauts, row for money. So if the coordinate system is here at the center, we can move this force up there to make it a little simpler. So the location of that force after I move it is negative 0.5 zeros. You get the same things whether you use the 0 here or whether you use the negative 0.15. Okay. But you can simplify things a little bit if you move the forces along their line of action. Save you a little time on the geometry. So the about point, since we put the coordinate system, since we put the origin at the center of mass, this is just zeros. Subtract, and the row vector is this. The force vector is, this is in the y direction, so 0, 200, 0. So the cross product, you get a moment vector of 0, 0, negative 100. Does that sign make sense with your intuition about? You can think about it two ways. One is with the right-hand rule. That moment, is producing a clockwise rotation, right? So it makes sense that would be in the negative z-axis. You can also think of it as clockwise is negative, counterclockwise is positive. Okay, so that all checks out. Do we need step 5 in this case? Do we need to use Newton's second law? Yeah. So we have 0, 200 is equal to 15 times I guess I'll write it as A COM X, A COM Y. Two equations. Step 6 is Rn2L. We're doing it about the center of mass. So 0, 0, negative 100, or I don't know, I'm going back and forth on this. Let's just do the z direction only for plain problems. So negative 100 is equal to 1.3625 alpha. This is a third equation. So here we have 3 equations, 3 variables, so we can solve right now. We don't need any constraint equations. And so you get the acceleration vector of the center of mass is equal to 0, 13.33. And the angular acceleration, I'll write that as a vector, is 0, 0, negative 73.3945. Anyone get those? Great. Okay, so you can think of those as sort of properties of the body. We're going to use both of those for parts A and B. So now we're going to branch off into part A, and I'm going to do this one, and we'll see it's exactly the same as that constraint equation for the last example. We're going to use relative motion equation, and we're going to use the circular motion equation. So this is actually sort of step 7, not sort of, exactly step 7. So the acceleration of that point A relative to the origin is what we want, is equal to the acceleration of A relative to the center of mass plus the acceleration of the center of mass relative to the origin. This is this. And the acceleration of A relative to the center of mass is alpha cross R plus omega cross R. Actually, last spring someone came up with a funny mnemonic device for that too, but I was jealous of their wittiness, and so I forgot it to spite them. I'll have to look back at my notes and see if I can find that. Okay, so alpha we have R. What's R going to be for that point A?
0.
Yep, 0, negative 0.5, 0. And what about omega? So that just has to do with, that's one of the initial conditions you're going to have to get, and I said that this is at rest at that instant. Ah, yes, thanks. Yes. I wasn't really listening to you, JP. Oh, okay. Okay. So I was justified. Okay. And I said that it's at rest at that instant, so omega is zeros. So the acceleration of A relative to the center of mass is 0, 0, negative 73.39 crossed with negative 0.500 plus crossing something with a 0 vector. This is all going to come out to be zeros. So for that acceleration of the point A relative to the center of mass, that's like what the acceleration would be if you had a pin joint at the center of mass. Okay. You get 0, 36.70. And so put that into the relative motion equation, and you get the acceleration of, so, you know, this now goes here. The acceleration of A relative to the origin is 0, 36.7 plus 0, 13.33. And so you get 0, 50.03 meters per second squared. Any questions about that? Yep.
It's not really about the math, but maybe I'm already supposed to understand this, but if it's not moving, so it's not changing with respect to time, how come the rate that it's changing with respect to time? You don't just get instant at the start.
Yeah. An instantaneous velocity and an instantaneous acceleration are independent of each other. Over time, there's a relationship, you know. So think of
like it's easy for me.
Yeah.
Maybe not easy, but I can understand it. Like when it's something's already moving, like if I just take a snapshot
Yeah.
of time,
Right.
then there's a certain change. But since the thing hasn't been moving,
Uh-huh.
it's about to start moving. So
Uh-huh.
there hasn't been any change.
Okay. Then
There hasn't been any change in speed or anything.
right. Well, think of it, if it makes sense, if it's already moving, think of it all as moving in a straight line with a constant velocity, because it might be, as far as we know. We don't have any, you know what I mean? I mean, imagine that, like, the planet's also spinning, but imagine the planet's just moving along like this, you know? I mean, there's no difference between still and moving with a constant, in a straight line with a constant speed. I don't know. Maybe that doesn't help.
The way I sort of think about it is, it's about to start building other
Yeah.
things, but at this moment, it hasn't done anything, but it's about to
Right.
accelerate very rapidly.
Yeah.
And that's how I deal with the velocity can be zero, but acceleration can be something because it's about to go.
Right.
Like if you've already got a graph of what it does over time,
Uh-huh.
follow that graph back until you hit time equals zero, and at that moment where it's not moving and its velocity is zero,
Yeah.
you can still come up with an acceleration.
Yeah, so velocity is equal to the integral of the acceleration. Okay, so what if, so this is, that last one was a feeble attempt at intuitive, helping you understand it intuitively. Mathematically, it's like this. So say this acceleration is some big thing, you know, and you want to know what its effect of on the velocity is at 2 seconds. Here's how you calculate it, you know, like what's that integral? It doesn't have any effect on this. It only has an effect if you integrate over a finite integral, you know. Any other questions? Okay, so calculate the acceleration of the point B. Solve this. So again, we're going to calculate the acceleration of B relative to the origin. That's the acceleration of B relative to the center of mass plus the acceleration of the center of mass relative to the origin. And this one is still 0, positive 13.33. The acceleration of B relative to the center of mass is alpha cross R plus omega cross R. So that's 0, 0, negative 73.39 crossed with, what's R in this case? Yeah, positive 0.5. This is all zeros because omega is 0. And you get 0, negative 36.7. And so the acceleration of B relative to the origin is 0, negative 36.7 plus 0, 13.33 is 0, negative 23.37. Okay, so one thing that's worth noticing is when you use the geometric constraint equations in that circular motion equation, I think I have mentioned this before, but omega cross r is a centripetal acceleration. So intuitively, that should always be 0 if the thing isn't rotating, okay? At the chosen instant. Which is the same as saying omega is equal to 0, and mathematically, you know, that makes sense too. Okay. Let me just sort of introduce what we're going to go into with this next after spring break. So linkages. This is interesting stuff. Partly, I think, because there are so many ways to apply this. Here is how I've used this kind of stuff in research before. I always did biomechanics research, and if you want to calculate, like, for example, what's the effect of like increasing strength in a certain muscle at a certain instant in a running stride or walking or whatever, the way I have seen it before is in like preoperative kids who have like neuromuscular problems, cerebral palsy or whatever, to calculate what the effect is going to be of weakening a muscle to stretch it out, or you know, if there's a way to, like, basically, like, what's the best kind of muscle surgery to help them walk more efficiently. You can do this kind of analysis. And so if you have a muscle that applies, like, we know where it attaches, and it applies a force to the thigh here and a force to the shin bone here, you can calculate what the accelerations are going to be of the body due to a known force there, you know, and this kind of stuff is used in sports medicine all the time. And so the way you're going to do it is, so linkages, I guess to define it, is just a set of rigid bodies connected by joints. And the way we're going to do it is just basically we're going to use Newton's second law, possibly, you know, depending on whether there's a fixed point or not. Like for this, in this case, we have one of these rigid bodies has a fixed point. The foot, right, is pinned to the ground. Everything else, even though it's pinned to other stuff, none of those points is fixed in the coordinate system. And so we'd only use, there's only one of these where we wouldn't have to use Newton's second law, and that's the foot. But we'll use Newton's second law, rotational equation for each body. And then the geometric constraints are basically each adjacent body must agree about the acceleration of a shared joint. So we're going to use the same two equations, the relative motion equation and the circular motion equation. And the idea is, so what's the constraint between the thigh and the shin bone here? Well, they have to meet at the knee, right? And so what we're going to do is say, what's the acceleration of that knee according to the thigh? Okay, whatever it is, that has to be the same acceleration of the knee according to the shin. Okay, and so we'll just go around the body, build this big system of variables and equations, and in the end solve for a set of loads, joint loads, reaction loads, accelerations, and these are going to be accelerations of the center of mass, and angular accelerations. Okay, and this stuff is useful, you know, it's useful in biomechanics, it's useful in robotics, any kind of machinery that has joints you can use this analysis for. Okay, any questions? All right, have a good spring break.